2.4, what we are doing. One of the more important things you're going to do, kind of sets up pretty much the rest of the year, a lot of it. It says slopes, tangent lines, and then derivatives. Much of what we do in calculus is based on the idea of a derivative. So it's kind of your first experience with derivative and what it is and what it means and how to find them. To start here, I want you to write the slope of the line through the 2 points shown below in number 1. So what I mean by this is you look at graph number 1. If we were to draw a line through those 2 points here, and I ask you to write an equation for the slope of that line, you need 2 points to write the slope of a line. We have those 2 points. This is our first point. That's our second point. Ultimately, this is where that slope formula comes from that you would have been using for a while now. So we're just going to basically rewrite the slope formula the way that you should be fairly familiar seeing it. So difference in y over the difference in your x's, right? So nothing really new there. Change in y, change in x. When we find the slope of the line, what B is saying is the slope of a line is the average rate of change of the y values over that given interval. So whatever this was, obviously this is going to be an x value of 0. Let's say this is like an x value of 10. Whatever my vertical change is here, divided by my horizontal change, that is an approximation for the rate of change of my graph anywhere between here and here. So let's say like this was in feet. Okay, the y-axis in feet. Let's say this is in seconds. A lot of what we will be doing is something like this, feet and seconds and graphs and such. So if that's in feet, that's in seconds. Let's say we increase from, let's say this was 2 feet. Let's say this point here was 4 feet. And we took 10 seconds to do that. What we would have just found is the slope of that line would have had a vertical change of 2, horizontal change of 10. So our slope would have been 2/10, which would have been a 1/5. That would be your average rate of change over the period of time from 0 to 10 seconds. What that's telling us is, if I ask you in any point in time in between here, what our approximate rate of change is, you could use this value to approximate the rate of change in this interval. All right, that's kind of what average rate of change deals with, okay? So when we find the slope, that's what you're finding. Down here, it says for graph number 2, so for this one here, it says let h equal the difference in x. What I mean by that is we have 2 points, here to here. I want to get from this point to this point. The difference in x shown here, the difference in x, would basically just means the change in your horizontal position. So what we're going to do, put your pencil here, put a little dot, and kind of do a dotted line here. This is our horizontal change. This is our change in x. We're going to let this horizontal change in x here, from this point to line up with that point, we're going to let that be h. That's what I mean by this. Let h equal the difference in x. With that now said, letter A, write the coordinates of the second point shown. So if this is my first point, x, f of x, and I now want to write coordinates here, the way we are going to be able to do this, if this was my original x position, and I increase that by h, that's my change in x, then I should be able to label this x coordinate as the original position x plus however far I moved to the right, and I would have moved h units to the right. So that this point I could label x, which is where we started, plus the horizontal change that we just did when we drew it in of h. So this coordinate, our x coordinate is h. This x coordinate we're going to say is x plus h. Our y value then, instead of saying y, here we said x, and then f of x just means our functional value at this x coordinate. So now, my y coordinate here we're going to write as f. We want our functional value at this x coordinate, which we called x plus h. That's how we can label that new point, based on the idea that we knew what one point was, and we knew how far over we moved horizontally. This would now become the x plus h, and then your y coordinate is f of x plus h. Okay? Looks weird, but it's just kind of a different way of writing the slope. That's what I'm going to have you now do in B. I want you to write the slope formula for the line drawn between the 2 points in graph number 2. So graph number 2, look at your 2 points now. Here's our original point, x, f of x. Here's our new point, x plus h, f of x plus h. We want to do the same exact thing we did with these 2 points when we wrote our slope. So you're going to take y minus y. In this case, that's going to be f of x plus h minus f of x, divided by, and then just like we did up here, you're going to subtract your x coordinates. Our x coordinates are these two. So you're going to do x plus h minus x. So this one minus this one. When you do this, nothing really happens on top. You can't really simplify that at all. However, on the bottom, you have x minus x. Those are going to cancel. And all you're left within your denominator is that h. This is nothing more than your slope, just like up here was your slope. It's just a little bit different notation. So this is kind of our old notation, new notation, kind of the algebra, geometry way. This is sort of the calculus way. So we're in calculus, obviously that's what we're going to be using. What we mentioned up here is what we are finding when you find the slope is the average rate of change. We talked about it at the top. It is the amount of change divided by the time that it takes for that change to occur. So it's basically the change in y divided by the change in x. Determined by finding the slope of a secant line. If you remember secants and tangents from your geometry days, secants cross twice. Tangents would just hit the, generally when you dealt with them, you dealt with circles. You're just going to touch it once, and that's it. That's a tangent line. So this is a secant line. If this parabola continued on or whatever, this goes through that twice. That's a secant line. So whatever the slope of the secant line is going to give us our average rate of change over the interval given. This will approximate the slope at every point in between the interval covered. So this slope up here, if I would say that was 1/5 like we did, that means on average this graph has a slope of 1/5 this entire time. So if we added up all of the slopes in between, divided by 10 on average, that's going to be your average rate of change, 1/5. Okay? So, old way of writing slope is this. This we will still use from time to time. The new way of kind of talking about slope, though, is with the f of x plus h minus f of x over your h. Okay? First couple problems, 3. You're just going to be finding the average rate of change. For the graph shown to the right, find the average rate of change and the number of flies between the 2nd day and the 8th day. So if you look at your vertical axis, 10, 20, 30, 40, 50, your vertical axis is measuring how many flies we have in a population. If you look at your, can't see that, there. If you look at your horizontal axis here, this is measuring how long it takes for those populations to change, so in days. And what we want to find is the average rate of change between the 2nd day and the 8th day. So here's the 2nd day information. There were 20 flies. Your 8th day, you had 46 flies. So if we just drew in a secant line between these 2 points, okay, between those 2 points, whatever the slope of that line is, would be the average rate of change of the flies during the 2nd day through the 8th day. And that's what we want to find here. So all we would be doing is doing our slope. So you're going to take 46 minus 20. That's the change in your y's, so 46 minus the 20 over your changes in x, 8 minus 2. That would equal 26 on top, 6 on the bottom, that's 13 thirds. Then we want to include units too, which would be a big thing throughout the course of the year. What our units would be, the 46 and the 20. So y and y would have had units of flies. The 8 and the 2 that we subtracted, the 8 and the 2 had units of days. When we divide those, you should get flies per day. So this would be 13 thirds flies per day. All right, 13 thirds is about 4, a little over 4. So that means on average, between the 2nd day and the 8th day, we increase by about 4 flies per day. All right, is what we do when we find that average rate of change. Number 4, given a new point, so 10, 20, so plot 10, 20. So here's 10, 20. Find the average rate of change between 0 and 10 days. So now draw in, sorry, here's 0 days, so at the beginning, 3 or 10 days. So we basically started with no flies, and we finish here at 10. I told you that point is 1020, so let's label that as 1020. We finished with 20 flies overall, okay, your population. We want to find the slope. That would be your average rate of change. So just like we did up top, you're going to do 20 minus, this is the point 0, 0. So 20 minus 0, that would have units of flies. Over 10 minus 0, that would have units of days. So on average, our average rate of change would have been 2 flies per day. So on average, each day we increase by 2 flies based upon that model. Okay. All right, now before we flip to the next page, okay, we kind of go into something a little bit different. This here is an approximation for how quickly our flies are increasing in any particular day. So if I ask you on the 4th day to give me an approximation for the number of flies, the rate of change of your flies on that particular day, you could actually give me either one of these answers. The reason for that is 4 falls in between the 2 points here, and it falls in between the 2 points there that we use to find the slope of our line. If I ask you on the 8th day what your rate of change was on the 8th day, it doesn't fall in between these 2 points, but this point does fall in between here. This one had a slope of 2 flies per day. So we could say on the 8th day, if I ask you what our approximate rate of change was on the 8th day, you could actually use this as an approximation, all right, because it falls in an interval. The reason that's not necessarily a good thing is because it's pretty clear here that the number of flies is decreasing this whole time, even though we're saying in this entire interval we were increasing by 2 per day. Over here you have a problem because our population is actually going down. So the average rate of change is an approximation tool we can use to approximate rates of changes over intervals, but ideally we could figure out what is our rate of change at each particular point so we don't have to kind of guess and end up with a bad approximation, which is what would be happening here. Here we're saying that we increase 2 flies per day, but very clearly over here we're decreasing in our population. All right. So even though there's a method to find a rate of change, it's clearly flawed. So what we want to kind of get to in the next page is finding exact rates of change on particular days. So that if I say on the 4th day, what's my rate of change, and you don't have to guess, you don't have to use one of these approximations. All right. And that's what we get to next. So now we can flip. Here, I want you to redraw the secant line through these 2 points. So draw that back in like we did on the front page. We'll label this point here the same way we did on the front page. So this is going to be x plus h. And this is going to be f of x plus h. Again, so go ahead and do that. Letter A, rewrite the slope equation the same way that we did on the front page with these 2 new notations. So it should look initially just like we did before. So your slope would be the f of x plus h minus f of x over h. All right, is the slope of that line, just looking at it, going to be positive or negative? Okay, hopefully we know that should be positive. Anytime we're increasing left to right, should be a positive slope. All right, what we talked about before, is this slope a good approximation for all slopes within that interval? You would say no, because there are times when this is saying we increase the whole time, this graph is going to increase the whole time in that interval, and very clearly our graph is decreasing this time. And then actually at this point, you would have a slope of 0, and wouldn't be increasing or decreasing. So to say over this interval that we're always increasing based upon this line is obviously a problem, because there are times where we're going to be decreasing. All right, and that's kind of what we would write in here. There are times when our y values decrease. They are not always increasing, which is what a positive slope would be telling us. Okay? So what we would like is this. We would like the instantaneous rate of change. Okay? The instantaneous rate of change will give us the rate of change at a specific point on the curve. So instead of doing it over 2 points like we did up here as an approximation, it's going to give us the rate of change at one particular point. It will be the exact rate of change versus an approximation, and it will be at a specific time instead of over an interval of time. It'll give you the slope of the curve at a certain point, and it's determined by finding the slope of the line tangent to your curve. Okay? The formula for this, we're going to have to figure out up here again. So go back to the top here. Draw in that little horizontal line H here. Okay, that we would have had. That's what's measuring this horizontal distance. Alright, next. Draw in a point here and draw a tangent line into this. Oh, crap. Okay, don't do that yet. Erase that. Erase. Okay. What I want you to draw in is just put a point here. Put it, doesn't really matter. We'll say that it's right there. Since this point falls in this interval here, we could use the slope of this graph to approximate what the slope of the curve would be right here. Alright? That's kind of what we talked about on the front page. However, like we said, this is not necessarily a good approximation because we have some negative slopes in here, a zero slope. We do have positives over here, but a slope of 2 is not a good representation of all these slopes. So what you're going to do is draw on a point right here. And what we would like to know is what is the slope at this point? So think about what would happen if we made these 2 points for the secant line a little closer together. So now it kind of looks like this. It forms this secant line. What should happen is if these 2 points are closer together, we could approximate the slope of this line using these 2 points as well, because this point falls in between both of these. Well, what should happen is if these points are closer together, you have less error involved, where you're now factoring in less negative slopes in here. So there should be a more accurate approximation by using these 2. Well, if we get even closer together, so let's say we pick these 2 points and connect those 2 points, then this secant line should offer us even a more exact approximation for the slope at this point. So that the closer and closer and closer and closer and closer and closer and closer we get with these 2 points to the point that we actually need, eventually they're going to become so close that when we draw our line in, we now end up with a tangent line. Okay? Whatever the slope of that tangent line is, would have to be the slope of the curve at that particular point. Okay? And that's kind of what we are now dealing with. So that's what I mentioned down here. It's going to be determined by finding the slope of the line tangent to the curve. What a derivative is going to do for us, an instantaneous rate of change, which is going to be your derivative, is going to do for us, up until this point, we've only been able to find slopes of lines. Positive slope, negative slope, flat line is a horizontal slope, so you're going to get a slope of 0. What derivatives do is when I now give you a parabola, or like a sine graph, cosine graph, if we want to figure out how quickly that graph is increasing or decreasing, if we wanted to figure out what the slope is, the derivative is going to allow us to do that. That's what derivatives do. They now allow us to find slopes, rates of change. It's going to become like if you think velocities are rates of change. You can now do this with much more complicated functions than just linear equations all the time. All right, and that's what we're dealing with. So, the formula for this. What you're going to rewrite, because we were still finding slopes of lines. So the slope of a line, we said before with our new notation is this. Change in y over change in x. They just look weird now. Right? The whole f of x plus h minus f of x over h. That's what we have on the front page. This on the front page we call the average rate of change. What we now want is the instantaneous rate of change. The reason this is now an instantaneous rate of change is because as these 2 points get closer and closer and closer and closer together, what would be happening to the horizontal distance h as our points get closer and closer and closer and closer and closer and closer and closer together to where they're pretty much right on top of each other. Alright? Now usually I would see if anybody could throw that out there for me, but what we're looking for is as these points get closer and closer together, this h, as it gets smaller and smaller and smaller, what we would write is h, as those points get closer and closer and closer together, should be becoming a 0. The distance between our 2 points should pretty much become a 0. So this now is why we do this after limits, because what we're going to do with this now is we're going to calculate the limit of our slope as the horizontal distance between our 2 points is going to get smaller and smaller and smaller and smaller. When we do this, this is in essence what we're doing. We're finding the slope of all the lines, and we're figuring out what limit do we approach as that happens. This is the instantaneous rate of change formula. Without that little limit, it's the average rate of change formula. That's what we did in the front page. That's an approximation. With this is your instantaneous rate of change formula. This is exact. All right? Okay, with that said, the next word is a derivative. All right, derivative is the instantaneous rate of change. It is the slope of the curve. It is the instantaneous rate of change of your function. So we will usually use this word, but these are all interchangeable. Instantaneous rate of change, slope of the curve is what the word derivative means. Okay? All right, pretty deep stuff. Any questions? No? Usually people have a lot of questions on this. Anybody? Anybody? All right, perfect. Moving on then. This is kind of what I just said here. Here's your average rate of change. There's your instantaneous rate of change. What we are now going to be doing here is finding the derivative of this equation, y equals x squared. Again, knowing that the derivative is your instantaneous rate of change, and we'll be using this formula because that's what a derivative is. Okay? All right, so give me 1 second here because I'm going to cut this off.